Welcome again to this beautiful channel. I'm your host, Shungu. So what we're going to do is continue or proceed with the discussion that we were having in the previous video, and that is about the thermal stability of group 2 carbonates and nitrates. So just a review here, we say the carbonates can decompose to give you a metal oxide and carbon dioxide gas. Your nitrates can decompose to give you your metal oxide, nitrogen dioxide gas, which is a brown gas, and oxygen gas. And so here you can see there is a way to confirm whether something that is thermally decomposed is a carbonate or nitrate. Here, if it's a carbonate, you're going to produce carbon dioxide gas, and you can test that gas using lime water. So it turns lime water milky. And if it's a nitrate, then you should see some brown gas, nitrogen dioxide, and some oxygen can also be used to confirm whether that was a nitrate. It can relight a glowing splint. So an experiment can be done to confirm just by using those products. So what happens? There's a trend going down the group for the carbonates and nitrates. The carbonates and nitrates, both of them become more thermally stable as you go down the group. This means that it becomes increasingly difficult to decompose these two types of compounds as you go down the group. It becomes more difficult to decompose nitrates or carbonates as you go down the group. So why is this so? You need to understand that in order for a bond to break, whether it's a nitrate or a carbonate bonded to a metal ion, there has to be distortion of the bond first. There's an electron cloud around this anion that is distorted by the charge on the metal ion. So the larger the charge on the metal ion, the greater the distortion. This charge around the metal ion, the factor that we look at there is called charge density, which is a comparison of the charge, the ratio of the charge to the radius or the size of the atom. So the larger the charge, if you have a large charge and a small radius, you're going to have a high charge density. If you have a large charge and a small radius, you have a high charge density. Conversely, if you have a large ion and a small charge, then you're going to have a small charge density. So we look at charge density going down the group. So what's happening is that as you go down the group, the atoms are getting larger and the charge remains constant. So the charge density is going to decrease as you go down the group. The charge density is going to decrease as you go down the group because the charge remains constant, yet our atoms are getting bigger. So when you have a large charge density, you are not going to be able to distort. When you have a small charge density, you are not going to be able to distort this bond a lot, and hence it becomes difficult to break it. So in order to break it, you have to distort it and then break it. So that's the way to think about it. So going down the group, our charge density is decreasing, and our ability to distort this bond, the anion, is decreasing, and hence it becomes increasingly difficult to break these carbonates. I hope it makes sense for you. So here we are saying the less distortion, the more stable the carbonate is. So you need to remember what causes the distortion. It is the high charge density on the metal ion. So metals low in the group, low charge density. Metals high in the group, high charge density. So meditate on that one. Okay, think about it. You can pause this video and go through what we just said. Okay, let's move on. So we also have our another example here, but this is group 1. So your group 1 carbonates and nitrates can also decompose to give you in this case your metal oxide and carbon dioxide gas. Lithium breaks down to give you lithium oxide, nitrogen dioxide, and oxygen as well. And here, in comparison to group 2 metals, magnesium 2+ has a high charge density and distorts the electron cloud around the carbonate or nitrate ion more than, for example, sodium, which has a lower charge density. So here the charge density is low because the charge itself is low, and regardless of the size of the ion, your charge is low, and hence you're going to have a low charge density for the sodium compared to the charge density on the magnesium. So there's less distortion with group 1 metals, generally speaking, than with group 2 metals. So less distortion, more stable. The more stable the carbonates. So we expect group 1 carbonates to be more stable than group 2 carbonates. I hope it makes sense. Okay, let's move on. So you can test for thermostability using what we looked at before. You can heat your carbonates or nitrates and see whether they decompose. You can measure the amount of gas produced per given time. You can, for carbonates, you can use lime water. You see the color change, how long it takes to get your color change. Your nitrates, you need a gas that can collect using a gas syringe or amount or the amount needed to relight a glowing splint. So you can use a gas syringe and see how much gas is collected per given time, or you can figure out how much is needed to relight a glowing splint. So an experiment can be done using a glowing splint there. Then the nitrates, again here, you can look at the length of time it takes until a specific amount of nitrogen dioxide is produced, which is a brown gas that can be easily observed. However, it's toxic, so this has to be done in a fume cupboard. So we have some flame tests that can be done also for the cations in group 1 and group 2, in which you need a nichrome wire, which is deep, which you have to dip in concentrated HCl, and then you dip it into a sample of the metal that you want to test, and then you place the loop on a blue Bunsen flame. And what you have is you're going to have different colors for the different ions. So yeah, the colors you can check: yellow, orange for sodium, lilac for potassium, red, etc. Going down barium, you get green color. So what causes the color changes that when you heat, the electrons in the ions are going to absorb some energy and they go to a higher energy level, and when they drop back, it's written here, when they drop back, they're going to emit some light, and this is why we get those colors. This discussion also comes back when we talk about transition metals, so hang on for that one. We'll talk about the color changes, why transition metals give colors when they are put into solution, when they dissolve in water, when they associate with water molecules. So we'll talk about it later on under transition elements. So we'll go to the halogens. So we're just going to scrape on halogens here and proceed in the next video.